Okay, greetings, friends. We're going to be getting started today in a way that tries to pick up from last time. Now, for those of you watching these videos, basically no time has passed, but for us, yeah. So anyway, we got a class this week. At least we got one in, so that's good. I'm going to go ahead and say that there's no PLC and no new lab. Now, last week, I posted the lab on Friday, and for some reason I've been having trouble getting the videos. I don't know what's going on, but anyways, I had some issues with the video, and I don't think I ended up making, I think it's working now, but I don't think I got it posted and available until like Sunday or Monday, and your labs due usually on Monday. So I just said take Saturday, and plus we haven't 100% covered the thing that I wanted to talk about anyway, which I was planning on doing. Although I did give you an introduction in the video. So lab this week, if you haven't done last week's lab because of the issues with the video, then go ahead and do that this week. And if you've already done it, good job. Thanks. So given our kind of later start this week, I'm just going to say no PLC, no lab going on this week. I need to fix up homework 5, which should pick up with ideal gas kinetic stuff that we've been talking about. And then hopefully today we're going to start talking about the second law a little bit more in detail. So I have a few odds and ends to finish up before we can move on, and we'll take care of that. See how we do. Now, last time, I think I remember we finished on an example. We talked about the mean free path, and we talked about the equal partition of energy, meaning the idea that energy, when in thermal equilibrium, energy is distributed equally amongst all ways a gas particle can have the energy. So let's pick up there. I'm going to say a few extra things about that, and we'll get one more example put in there, and then I think we'll move on to the second law and start talking about that. So in terms of equal partition of energy, I told you, I think, that what we do is count modes. So the idea is that when you have a gas that's in thermal equilibrium, which is essentially what we deal with, we don't really deal with non-thermal equilibrium, non-equilibrium situations. So anyways, but just to let you know, the idea is that the energy is divided, or there's the same amount of energy every single way a gas molecule could have energy. There's the exact same amount every way. So energy is divided equally. I guess I don't know if divided is quite the right word. But anyways, it's divided equally amongst the, say, available modes. And I talked to you last time about counting those modes in the guise of thinking about how to calculate the molar specific heats of the gas. You remember this? I don't. No, I do. It's okay. So we talked about CV being the number of modes available to the gas molecule multiplied by 1/2 R. And that means that for a monatomic gas, which is just basically a ball, it could move in the 3 directions, and therefore it would have 3 modes. And when you had a diatomic gas, which is not this, but instead it's 2 balls connected by this, like so, it's like a barbell, right? And now it can not only move in the 3 directions, but it can also rotate, like so, in around 2 axes. So the number of modes is basically like the number of ways a molecule could have energy. I usually think of energy as water, and the modes are little containers, and what you're doing is you are the distributor of the energy. So you're pouring equal amounts into all of the available containers. Okay, I mean, it's kind of like, I don't know, it's kind of like going to the kid's birthday party, right? Nobody wants, you get your little Dixie cups. No one wants to come away with a Dixie cup that's only like half full. You got to fill them all the way up. That way there's no problems. So the number of modes is equally filled, and our job is to try and count how many there are. Now, the minimum is 3 because we live in a space of 3 dimensions. So that is always kind of the floor that we have, and then we're going to be adding on top of that. So for the example of 2 rotational modes, each one of those has the same amount of energy as one of the translational modes. All right. So the idea is that the amount of energy per mode okay, this is now energy. That was molar specific heat. Now the amount of energy per mode is 1/2 kB times T. And kB is the Boltzmann constant. This is a name we will run into again. Not constant. Boltzmann is the name we will run into. Therefore, if we are interested in calculating the total energy in the gas, we would say, okay, all I've got to do is take the number of modes multiplied by this, and then the number of molecules multiplied by that. And then you'd have the total energy in the gas. In other words, number of modes multiplying 1/2 kBT. This is the amount of energy per molecule, right? And then times capital N, which is the total number of molecules. Let's take an example of, let's say it's just a monatomic gas, like helium, right? It can only move in the 3 directions. There's no rotation. Therefore, I'd have 3. I'd have times this, which would be 3/2 times the kBT times N. Okay, now if I have 3/2 N kBT for a monatomic ideal gas. If you remember that the NK is the same as little n times capital R, you could rewrite that and say it's the same as 3/2 times nRT. And then you'd notice that we were back to the same idea of this is the energy in the gas. This is the way that we calculated the kinetic energy in the gas, right? Or if you like, 3/2 times PV, whatever you prefer. And so this would be the total kinetic energy, because the kinetic energy is the energy in an ideal gas. Alrighty, now what this means is that sometimes we have modes that are active and sometimes we don't. So if we have modes that are active, typically what will happen is this is some size relative to the spacing between the activation energy that's required for a particular mode. All right, so in other words, if I say, all right, I'll just let me just diagram this out for you. So suppose that, right? Solid state physicist loves the energy level diagrams, the bar level diagrams. Suppose that that's diagrammatically as much as 1/2 kBT is. Okay. In other words, like I'm thinking about a ball and I'm going to take it from this shelf and put it on that shelf. What's the increase in gravitational potential energy? Same kind of idea, right? I've got a certain amount of energy here, okay? And that's the energy that each mode could have. So suppose that we have, I'm going to label translation and rotation. Suppose that we have the translational modes. Suppose we have, I don't know, we have like, we have 3 translational modes. They all have the same energy, right? They all can get put with the same energy. So if I have my 3 translational modes, which I'll just call 3T here. Wait, this isn't, I don't like the way I'm doing this. I don't want to have 1/2 kVt here. I'll take that away. I want to have, actually, yeah, take this away for a sec. So suppose that I'm doing this is total energy. Maybe this is total energy, this would be better. Okay, sorry. Suppose that I've got the total energy, then 3T's not down here. Okay, then 3T's right here. All right, so I've got some amount of energy in the gas. Suppose that my translational motions were that much of it, right? In other words, the total energy in the gas, whatever it is we calculate here using the number of modes and the number capital N and all of this stuff, is that much. Okay, and you're thinking about how to divide it up. So if I have 3 translational modes, I have a certain amount of energy in that. Okay, they're all filled up the same amount. Okay, and then say that I'm going to have 2 rotational modes, which I'll call 2 Rs. In other words, like a diatomic and a rotation this way and a rotation that way. Okay, so I'm going to have 2 more that way, and now I'm going to have 2 more in the vibration. That's capital V right there. So what I'm doing is I'm thinking of the total energy in the gas as being composed of, all right, suppose I have all of these translational motions going, I have 2 of the rotational motions going, and I've got the vibration going. I've divvied up the energy, right, so that they're all adding up to make the total energy, okay? Now what happens if I think about, okay, suppose that instead of that, what I'm going to do is zoom way in, right? Suppose if I zoom way in, the total amount of energy is less. Suppose I reduce the temperature, right? And I say, okay, I'm going to cool the gas off, and we're going to see what modes are available. Okay, so so you can see as I cool the gas off, what's going to happen is the first thing is these vibrational modes are going to go away because the total energy is not going to be able to fill this piece right here. So as soon as this blue line dips underneath this line here like that, then these modes are no longer active. And as soon as the blue line dips underneath the rotational one here, those modes are no longer active, right? So as I reduce the temperature, and this starts to fall, then I start it's called freezing out of the modes. Like, because the temperature is going lower, so you're thinking of them as freezing out. Nothing's literally freezing. It's just that these modes are no longer active because the amount of available energy you have has dropped. I can't get the ball up to this shelf here anymore if the maximum I can get is there, right? This is like trying to think about, well, I got another, there's a floor above me. I want to throw a ball up to that floor, but I keep hitting the ceiling. I can't get the ball up there, right? So there's no possibility for the energy to get these modes active because there's just not enough of the energy to do that. Anyway, so that's what equipartition of energy does. I want to do one other thing, which is talk about the way to recognize monatomic versus diatomic versus polyatomic. We've already talked about how to do that in terms of the number of modes. So like I said, the bare minimum number of modes is 3. You go to a diatomic molecule like air, it goes to 5 if you have the right temperature. It goes to 7 if you have a higher temperature. But if you have a more complicated structure, then you might have, instead of 2 rotational modes, you might have 3 rotational modes. Or instead of 2 vibrational modes, when you get to higher temperature, you might have 4 or 6, something like that. I want to explore a little bit more of that. And do a quick example, and then we're going to jump into the second law. And we're going to go from there. Now, so this is kind of goes under the heading of distinguishing between I don't know if type of gas, not chemically, but structurally, what type of gas is it? Monatomic, diatomic, polyatomic, right? That type of thing. So I'll call this distinguished between gas molecule structures. This is really interesting because chemically, of course, you know, the chemists can take care of, oh, this is an oxidizing type of gas, this is a reducing gas, this is a blah, 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 oh, the pH, that, right? They have ways of distinguishing, okay, great, this one weighs more, this one weighs less, cool. We're actually interested in something a little more basic than that, which is, what do they look like? What kind of structure do they have? So, monatomic, I drew you up this last time, monatomic is just a ball, right? And then diatomic is the barbell. And polyatomic is just more than 2. I think the one I drew for you last time maybe was something like this. It's some kind of triangular doohickey thing like this. It's polyatomic. But polyatomic could be a lot of different things. This, for example, polyatomic is just greater than 2. That's all it really means. So here's 3. You could, for example, have Mickey Mouse ears, which is the water molecule. Like, for example, if I took this bond away because the hydrogens aren't bonded in the water molecule, so I'd have an oxygen with 2 hydrogens. Or I could think about NH3, which is ammonia, so I have the N here and then 3 H's like this, and then you can think about what structure is kind of pyramidal. Anyways, those are polyatomic, so one example is this. It's not the only example, but you can see with this one I'm going to get more rotational modes, and I'm going to get more vibrational modes than I would in the diatomic case. So number of modes, whoops, I meant to put that up there, but anyways, okay, in this case it would be 3. Monatomic is 3, and that's 3 for translation. In this case, we'd have 3 for translation, 2 for rotation, right? Possibly. Also possibly 2 for vibration. I'll put question marks near those just because they depend on the temperature of the gases. Typically at room temperature now, air is going to have 5 modes. You'd have to get up to a higher temperature, like around a couple hundred degrees before you got the vibrations excited, if I remember correctly. A polyatomic, again, 3 translation. I'm just going to use T for translation here like I did over there. I could have 3 for rotation in this case. I'll question mark that one because, again, the temperature has to be high enough. There has to be the right amount of energy available. Okay, right? The minimum amount's going to be this. So as I start increasing the temperature and I start saying, oh, the amount of available energy is going up, 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 I don't do anything until I can activate all of the rotational modes. One of them doesn't activate before the others. They all activate at the same time. That's why the jump. So 3 R's. If you had this and they all had the same type of bonding, you'd have 2, 4, 6 vibrationals. I'm going to, again, put a question mark near there because the temperature would have to be high enough. One way to distinguish between these is, right, to know the number of modes. So how do you know the number of modes? one thing to do would be to measure the specific heats, right? The molar specific heats. If I measured the molar specific heat and I found it was 6R, oh, well, maybe I'm talking about a polyatomic. There is one other quantity I want to introduce you to, which is called the gamma factor. And gamma is the ratio of the pressure, the molar specific heat at constant pressure to the molar specific heat at constant volume, like so. Now, notice what this does for us, okay? You know that Cp is the same as Cv plus R. In other words, we already established that these two things are equal. So what happens when I divide by Cv is that I can rewrite this as 1 plus R divided by Cv, where Cv was what I wrote up here before. It's the number of modes times 1/2 R. Therefore, I could really rewrite this as 1 plus 2 divided by the number of modes. And this is rather convoluted of a way of distinguishing between what type of molecule I have in the gas. Now, for example, let's take a look at a regular monatomic ideal gas. If it's monatomic, okay, then what I have here in the Cv would be 3/2 times R, right? And what I would have in the Cp is 5/2 times R. Well, so you got two, you can do it a couple of different ways here, right? I could say number of modes here is, since it's 3, what I'm going to do is say 1 plus 2/3, well, that's 5/3. Because the molecule doesn't have more than 3 modes and it never will. I could see the same thing from dividing Cp by Cv, because I know Cv for monatomic, I'm sorry, let me note that this is for monatomic. That's for monatomic. And so if I go back to the very original definition here, I would have Cv, which is 3/2 plus R here, which would give me 5/2 R, right? If I look at Cp for an ideal gas, for a monatomic ideal gas, I'd get 5/2 R. I divide by Cv, which is 3/2 R, and then you'd notice I get the same 5/3. Okay. If I were thinking of a diatomic gas with rotation, then my number of modes would have gone to 5, and I'd be adding 1 plus 2/5, which is 7/5, and that is not the same thing as 5/3. If I went to a diatomic gas with rotation and vibration, well, you'd be able to distinguish between that, because you'd now be looking at this number being 7, and I'd be looking at 9/7. 9/7 instead of 7/5. If I had a polyatomic gas, well, there's a bunch of other ones that it could be. So monatomic 5/3, diatomic, let's look at this, where it would be 7/5, could be 9/7, question mark. Okay. Ultimately, if the diatomic gas has only the 3 rotational modes, you can't tell between monatomic and diatomic. The diatomic's acting like one big unit, which means it's just moving around like a monatomic gas. You'd have to heat it up in order to activate the rotational modes. Now, these are the ones that it's useful to keep in mind. And then if you find a gamma which is not one of these, then you know it's something else, probably a polyatomic case. Let's take a look at an example and see if we can determine what we have as a gas. Alrighty, so let's do this. Incidentally, I don't know whether I mentioned this. I said we were going to get back to some of the more mathematical things about the adiabatic process. That gamma factor plays into the description of the adiabatic process. Okay, let's suppose I have a gas here. Of course, an ideal gas. Let's suppose that we have a gas undergoing what's called free expansion. Free expansion is a situation where I have a container that's divided like this, and I have a gas on one side. And I have a vacuum on one side. It's a rigid container, so it's not going to flex. But this membrane right here is rupturable. In other words, I can somehow remove it or puncture it or something. Okay, suppose I got a little apparatus in here, it just goes conk and it knocks it over or knocks it out, right? So that when I rupture this membrane, the gas can expand. I'm going to say it's breakable. Maybe a breakable membrane. First thing I want to think about here is if I break that membrane, the gas expands into the new volume. Okay. What's the change in internal energy of the gas? What's delta E during this process? What is delta E internal? Right? Is there a change in the internal energy of the gas as it free expands? Okay. Suppose that I didn't really draw it super well, but suppose that the volume into which it's expanding is, I don't know, 2 or 3 times bigger than what it was initially in, right? So this would be, the way I drew it here, this would be doubling the volume. What pressure would we be talking about in that case? After the rupture of the membrane. Two or 3 times bigger. Let's say 3 times bigger. I didn't draw it that way. But I can. Let's just say it's 3 times bigger. So we're looking at something like this. Okay. There's a vacuum over there. No gas over here, no nothing over here. This is a rigid container. And all I did was puncture that membrane. So now it's no longer here, boink, there it's gone. And now the gas in here can flow in there freely. Question is, what happens to the internal energy now? The gas expands. So shouldn't the internal energy be dropping? Because we all know that when a gas expands, it cools off, right? Or if you like, it must be the opposite of what happens when you compress a gas. If I compress a gas, we know it heats up, okay? So if I expand it, it must be cooling off. Okay, but there's a difference. Why is that happening? Why, when I compress a gas, why is it heating up? Well, am I heating it up? Am I literally putting energy in via heat? No, I'm not, right? It's a bicycle plunger. So if I compress the gas, I did work on the gas. In other words, I increased the energy of the gas through not heat, but work. Yeah? And therefore, you could say this. You could say the opposite. when the gas expands, what does it expand against? Well, the pressure of the atmosphere. It does work, right? Like if I'm thinking about a balloon. I have to right? I have to blow into the balloon in order to get the skin to expand. Okay, partially that's because it's an elastic skin, but also it has to move air out of the way in order to expand here, right? There's air here, and here comes the balloon skin. Get out of the way. Therefore, as it expands, the balloon does work in order to move the atmosphere out of the way. So when the gas expands, suppose I have a really compressed gas and I let it expand, it's pushing its way against the pressure of the atmosphere. In doing so, it does the work on the atmosphere, which means that its internal energy is lower. Okay? Therefore, this is why we have these mental cues about what happens to a gas. If I compress it, it heats up. If I expand it, it cools off. Okay? The reasons are because there's work being transferred and not heat. Okay, but let's look at this situation. Is work being done on or by the gas? All I'm doing is I took it from a confined situation here, and I am now allowing it to occupy a bigger volume. But there's nothing over here that necessarily has to be pushed out of the way. You see what I'm saying? If there was a gas over here, or if there was something over here that had to make way in order for this stuff to come busting over here, then this gas has done work. But there isn't anything over here for the gas to do work on. So the gas just kind of floats in here and goes, oh, hey, some more volume, right? It's like I don't know, baby chickens or something. You got them in a small volume, and then all of a sudden you go, oh, look, I go to open the door and they wander in. And there's no work that they need to do. They just walk through the door and go, oh, cool, new area. So the change in internal energy in this case is zero because there's no heat transferred and there's no work done. So by the first law, both of those things be zero means this thing is zero. So anyways, hopefully that's a reasonable explanation. Question here is, what's the new pressure if the volume is 3 times bigger? Okay, well, if we know that the internal energy is zero, the internal energy change is zero, what do we know about the temperature of the gas? Well, there's no reason that the temperature of the gas isn't exactly the same as it was, right? In other words, this thing here is the marker for temperature of the gas, right? If I think of this molecule right here, it's moving around, and if I rupture this membrane and all of a sudden the thing starts going that way, well, fine. No big deal. There's nothing there to slow it down or speed it up. Therefore, the temperature is constant. This is essentially an isothermal process. Therefore, if I call it isothermal, what that means is that if I look at the equation of state, PV equals nRT, T is constant, therefore the PV is constant. That means I have the ability now to take PV, which is a constant number no matter what the situation, and take it before I rupture the membrane, and then I take it after I rupture the membrane. In other words, all I got to do is do P1V1 equal to P2V2. Right? This is before, this is after, and what I'm interested in is basically what's pressure 2. Well, that's easy enough. Pressure 2 is just the ratio of the volumes times pressure 1. Now, V2, this is V1 divided by V2. V2 comes over and I multiply by P1, and therefore if volume 2 is 3 times bigger, then pressure 1 is 3 times small. Sorry, pressure 2 is 3 times smaller. 1/3 P1. All right, perhaps no big surprise there. All right, now let's suppose that I now take, by the way, you'll notice an absence of a PV graph here. Reason being that you can't really plot a free expansion on a PV graph because there's no there's no equilibrium states other than the first one and the last one. So really a free expansion is just one dot here and one dot here. So there's no process for me to plot on a PV graph. But let's suppose now that here is volume 1. Suppose here's V1 and 3 times away is V2. That's over here. Okay, so there is a pressure up here and then there's a pressure down here and there's your free expansion, right? 1, 2. I can't connect them with a line. I can't connect them with, in fact, any type of curve because I have no idea what happened. I have no idea how it got from 1 to 2. So all we know is that pressure 1 and volume 1 and pressure 2 and volume 2 are related by this. So suppose now that we compress the gas and we take it and go, okay, now I'm going to insert a movable piston and go and compress it. But I'm going to do it adiabatically. In other words, no heat in or out. Okay. So I'm going to take it back here and I'm going to say, all right, this is an adiabatic compression. Where do I land when I get back to the original volume? Suppose that's adiabatic. And my question is, what's the pressure when I get back to the original volume? After adiabatic compression. Oops, not after. Yeah, after. Find pressure after reaching volume 1. Okay, when I get back to the original volume, I should have put original volume. Volume 1. It sounds like I'm reading a book. Okay, so this is where the gamma factor is going to come in. You're wondering what the segue is. I'm going to tell you right now. I was talking about how to identify a particular species of gas molecule right before this example, and then I jumped into this thing which seemed to be absolutely not connected at all. Well, here is where it's connecting, right here. We know, let's suppose we know something about what structure this gas has. Let's suppose that we know so let's suppose, what type of gas is this? Well, if we had something whereby we know the gas is, let's do something a bit more well, no, let's just do it diatomic. Let's just say it's air for now. Let's suppose the gas is diatomic. All right? With rotation. In other words, its gamma factor is 7/5. How do we mathematically describe an adiabatic curve? Well, this is where the gamma comes back in. Now, for an isothermal process, this is true. It turns out for an adiabatic process, what's true is PV, not by itself, but PV to the gamma is constant. Oops, I'm off the board here. Where the gamma is the exponent on the V. Right? Isothermal is this, P times V, right? So I can take it to state 1, set it equal to state 2. I'm going to do the same thing with this quantity here, PV to the gamma. What is it at state 1, set it equal to that at state 2. Note, however, that the gamma acts only on the V, not on the P and the V, just the V. We've done all this, so let's get rid of that. P times V to the gamma is a constant, so let's take a look. If I have P1 times V1 to the gamma, and gamma is 7/5, right? That's what this tells us based on what we were just doing prior to this example. That means I should be able to say that P2 times V2 to the 7/5 is equal to P1 V1 to the 7/5. We know what well, I should say 2 to 1, 1 to 2, maybe I should say 2 to 3. Maybe that's what I should do. I'll call this state 3 right here, because we don't know where it is compared to state 1. All right, okay, so I'm going to backtrack and call these 3. Okay, sorry about that. My goal essentially is to solve for P3. I want to know what is P3 when I get back to V1. Right? When I get back to V1. So we know what V2 is in terms of V1, and we know what P2 was in terms of P1. Right? Up here. So what I can do is find out how much of P1 is P3. Let's try and figure this out. So we know we gotta keep this figured out here. This is V2 is equal to 3V1. And V3 is equal to V1. All right, so we know that. P2, we know it's equal to 1/3 of P1. And this thing, we have no idea what it is. And in fact, that's good because we want to know what that is. And now we'll get some ratio of how big the pressure is compared to the original pressure that I started at. That we started at, not just me. You're involved in this too. All right, let's take a look. P3, therefore, if I swing the volume over here and I have the P2, so I have P2, which is 1/3 of P1. And now I'm going to swing the V3 and the V2, and they are to the 7/5, so I've got 3, essentially 3 to the 7/5, is that true? 3V1 divided by V1, that whole thing to the 7/5, because both the volumes were to the 7/5 power. All right, these volumes go away, so this becomes P1 times 3 to the 7/5, and there's 3 to the -1 right here. Like that. So I guess that becomes 3 to the 2/5. Therefore, the original pressure is much greater because the adiabatic pressure, when I adiabatically compress it and I don't let any heat out, the pressure only returns to 3 to the 2/5. I have no idea what 3 to the 5th root of 9, I don't know. It's probably some small number. But anyways, it's less than 3. It's less than 1.
It's 1.6.
It's 1.6. Okay, it's not less than 1, it's 1.6. Cool. 1.6 P1. Oh, it's 1. So I'm totally thinking of the opposite. It's more, oh, so my diagram's wrong. I should have, therefore, state 1 should be about there. There you go. Ah, see, you learn something new every day. Cool. 1.6. So the gamma factor, this thing here, right, this exponent, is a small snippet of information as to what kind of structure the molecule has and what modes is it operating within. And that's really useful. So when you get to adiabatics, right, this is the condition. And when we went through ideal gas processes the first time, and we talked about the isobaric ones, the isovolumetrics, talked about the isothermal, and we had math expressions for all of the works, right, and the heats, and we did the isothermal ones, and we looked at the work, and with the work for the isothermal one turned into that natural log. And I just said, and by the way, there's this adiabatic process, it's this. Well, this is the reason we didn't talk about it right then, because this gamma is a kind of intricate quantity in the sense that it carries with it some specific information that it's nice to know. I don't know, but we could have probably have talked about it just then. But anyways, the point now is that it relates to the number of modes. Okay, so the number of modes is embedded in this gamma, and that's what the adiabatic process looks like. All right. Other than that, that's really all we need to know about the adiabatic process mathematically, and that's why the curve is steeper than it is for an isothermal. Alrighty. So, which makes sense why 3 is greater than 1. Of course it is. All right. Good. So we've got that. All right. I'd like to get on to a bit of second law stuff then, because I think it's a good time to. And anything else on this that would be interesting to know? All right, let's get back to the second law. We've examined the first law and some offshoots of the first. I mean, you can tell we're still using the first law. We're still using the first law, even back to this thing here, where I was talking about what the internal energy change was. And you use a little bit of first law reasoning to say, hey, there's no heat transferred, there's no work done. Therefore, the internal energy change in this process is 0. That's what the first law gives you. It gives you the ability to think about, well, if I had work or heat going in or out, that's changing the internal energy, or at least it can change the internal energy. Let's get to the second law now, which puts restrictions on how the energy can flow. If you remember the beginning of this whole thing, when we were done with optics and I started telling you about the laws of thermodynamics, I gave you 3 forms of kind of 3 statements, maybe it was, about the second law of thermo. So you can go back and look at those, I guess, or not. But anyways, the point is that we know what they are, and they were different. For example, the Carnot statement is slightly different from the Kelvin statement. And the Kelvin statement is a little bit more, it's a little bit more direct, because Carnot didn't have the first law in place already when he kind of started discovering the second law. By the time Kelvin came along, Kelvin did have knowledge of the first law, and so was able to say, okay, a bunch of the things that Carnot said would be excluded by the first law anyway. Let's make the second law a little bit more streamlined. Okay, so it looks like it's a subset of the Carnot statement. In other words, the Kelvin statement of the second law looks like a subset of the Carnot statement, and in some sense it kind of is, because Kelvin is assuming the first law. However, both of those statements look pretty drastically different from the Clausius statement. The Carnot and Kelvin statements were geared towards it's not possible to have a cycle whose only outcome is to exchange heat with less than one or less than two reservoirs, if it's Kelvin, less than two reservoirs, and produce usable work, right? The Kelvin and Carnot statements are about how do you exchange heat with the environment and produce work. The Clausius statement was more along the lines of you can't have heat running backwards. Heat doesn't go cold to hot. That will never happen, right? I think his statement was along the lines of a cyclic process is if you have a cyclic process whose only outcome is to run heat from cold to hot and nothing else, that's impossible. All right. So the key word in any of those three statements is impossible. And that's what makes the second law of thermodynamics the most powerful law in all of physics. It is the use of the word impossible, and it gives the energy no choice. Like, you cannot do this. I mean, it's like it's the governor and it's telling me energy what to do. Yeah, great. This is really the situation. We figured out that energy doesn't do what this type of thing is, and so we say it never happens. What I'd like to do is show the equivalence of the two statements. And this is a little bit of funsies. Because it relies on some interesting reasoning, which is kind of a little bit at the heart of thermo that I want to introduce you to. Show the equivalence of the second law statements made by, let's just say Kelvin. Let's just say Carnot. Let's say Carnot and Clausius. I want to get back to some of the diagrammatical stuff that I did when I told you about these statements. So just to refresh you on that, because it's probably not first in your mind, is that the Carnot statement was saying that the results of a cyclic process, remember he didn't know the first law, has, what did I say? The production of usable work by a cyclic process cannot be such that the process exchanged heat with fewer than two reservoirs, right? So, or really fewer than one reservoir is what Carnot said. So what that does is it excludes things, okay? So fewer than one heat reservoir. So remember, this is our cycle. And a cyclic process is one in which the original state variables are reattained after going through some set of processes. If I look at a PV graph like this and I say, how do I make a process? Well, what you do is you say, oh, well, look, I went from here to here, and then I went from here to here, and then I went from here to here, and then I went from here to here. And now I'm back at this original state right here. And that's a cycle. Whatever these pressure, volume, temperature was at state 2 when I started, now it is that again. And that's what a cycle is, and that's why it's represented with the circle here, because you're reattaining your original state. All right, so in other words, I should say same state variables. Finally, as initially. Okay, note that that doesn't mean nothing happened. There was definitely a process and a set of processes in which work was definitely done, right? there's work done because it's the area in that shaded place right there that I just done, right? That's the usable work that the system has given us. Therefore, it also must be, by the first law, the heat that you had to put in order to get the work out. Because if I have the same state variables in the end as I did in the beginning, then the energy change must be zero. What this thing implies is that delta E internal is equal to zero. Because it went through a cycle, and therefore Q is equal to minus W. Or W is minus Q, whatever. They're same quantity, same magnitude, but one's going in and one's going out. All right? So this circle means a cycle, and we're gonna do examples of things that are not true according to the Carnot statement. Examples of impossible processes. Right, according to Carnot. Now, this is not an exhaustive list. I think if you did diagram all these out, there's like 22 of them. I can't remember the exact number, but anyways, there's quite a few. For example, that is impossible. A cycle whose only result is to produce work. Well, you can't have that. Because the internal energy change should be zero. My work is coming out of nowhere. This is, you look at this and you just laugh. Right? It's just like, yeah, sure. This is really good. I'd love to make this happen. I would be the richest person, the most powerful person in the entire world, in the entire universe, if I could make this happen. Okay? Not only that, I would control everything. And anyways, okay, doesn't matter. So same idea, right? If you have something like, for example, heat going into a cycle and nothing else happening. Oh, that's not, you can't do that. Okay. Okay, also can't do this. Interesting, right? Interesting. This is a situation in which Q and W are the same size, even, right? Even if Q is equal to W. This is not an allowed process. This is fewer than two reservoirs, or fewer than two reservoirs. So you can't do this, even though it obeys the first law. And this is the thing that Kelvin was specifically addressing in his statement. Okay, let me introduce you to an idea here. Actually, a couple of ideas, in which what I would like to do is suppose that I have something like this. Now, we already know that if Q and W are not the same size, this is already not reasonable, right? Because according to the first law, we have to have this. So even if Q and W were not the same size, we already know this is excluded. So let's pretend. Let's play a game of pretend. Who likes to play pretend? Let's play a game of pretend with this thing. Let's suppose that I could have this. This is known as the contrapositive. In other words, I know this is wrong, but let's suppose it's right. I'm going to put that down a little bit further. Suppose let's say that. Let's suppose that the amount of work I'm getting out is more than the heat I'm putting in. Suppose this was a thing I could do. Well, I don't know why I used was. Suppose this whole situation is possible. Suppose that's possible. All right, I know. It's okay, bear with me for a minute. I'm gonna take this and I'm going to show you a couple of things. Number one, for any of these cycles, for any of these diagrams, you can flip them around. In other words, this is impossible, and it would also be impossible if I had the work going in. And same with this. Instead, I had the heat leaving. Or if I had the work going in and the heat leaving. It's impossible. So they're all impossible, right? Kind of like, well, that one's not quite so impossible, but point being that it's if it was not the same, right? It would be not possible. So let's assume that they're not possible. What I'm going to do, so the first thing is reversibility, right? I can reverse some of the arrows. The second thing is I'm going to start adjusting and linking two of these together. I'm going to kind of do a little bit of visual addition here. Let's take this one. In this case, I've got work being bigger than heat, so I'm going to maybe reduce my heat arrow a little bit to make it visually a little more obvious. Heat's a little bit and work's more. Now I'm going to take this and I'm going to take another cycle, which is the opposite of this one. In other words, I'm going to take this one, Q and W. I'm going to add to it, right? So that's this one. I'm going to add to that one. I'm going to add to it another cycle in which I'm going to take this much. I'll call this the prime cycle. So I got W prime over here, and I've got Q prime leaving, like so. All right. The size of the circle makes no difference. I drew a smaller one here. The size of the circle makes no difference. What I'm doing though is I'm tuning or adjusting, if you like, the sizes of the quantities. In other words, in this one, I already told you that the work coming out is going to be greater than the heat going in. In this one, I'm going to say they're equal. Let's have the work going in be equal to the heat coming out. And let's make the heat coming out the same as the heat was going in over here. Let's make W prime equal to Q prime in this situation here. So I've got work coming in, heat leaving. And let's make that equal to Q, which is the original amount of heat that was input in the first place. Now, if I add those two together, can you see what I'm going to get? This is the other part. So this thing here is called a cycle adjustment. I got to slow down a little bit here. This is called a cycle adjustment. So I've done a cycle adjustment, and now I'm going to add the cycles together. What's my total outcome? Now, in other words, I'm going to look at, instead of seeing two different processes here, I'm going to look at what's going in and what's coming out of the net situation of both of them, as if I'm taking both of them and just kind of smearing them together. What's the total outcome here? Well, let's look. Heat went in here, equal amount of heat left here. So the amount of heat net is 0, right? This came in, that left. It's the same amount according to my adjustment here. Therefore, what is this in its more simple state? There's a larger amount of work leaving here, but this one didn't require quite as much work. Therefore, of the total, I have a net amount of work leaving. Yeah? So this whole thing equals something like this, which is basically that. Yeah? Now, I supposed that this was possible. That tells me that if this is possible and this is possible, then this should be possible. But we already know this is not possible. Therefore, this is not possible either. This is not possible either. Okay? We already know this is not possible, therefore this is not possible. So this is known as argument by contraposition or contrapositivism, not contraposition. I don't know. There's some name for it. Go ask a philosophy person. The point is that I'm assuming, hey, let's guess that this is possible, and then when I find out that the results are not possible, that invalidates what I supposed. Therefore, this is not possible. I can't have something that does this. Okay, I get it. We already knew that. But I'm showing you because of the process of argument. Okay. All right. So a couple of takeaway points here. Cycle adjustments, and you can add these cycles together to get a net result. And that net result can be compared to other cycles. Okay. So let me do one. I think maybe, do I have a little bit of time left? Maybe I got a couple of minutes. Okay. Let me do one here in which it kind of helps with the original thing that I was doing up here. So let's take, I want to show you that these two are equivalent. Let's see here. This is what I want to do here. Okay, so now having done all of that, let's do this. Okay. Oh, by the way, if you remember Clausius, well, actually, never mind. I'll show you what Clausius is in a minute. All right. Let's take this and let's do the same thing. Let's suppose that this is possible. Okay? We know it's not. Let's suppose that it is. It's a fun game. All right? Now, I'm going to take that and I'm going to add it to a situation in which I have, this is the hot reservoir here, so this would be QH. This is the cold reservoir down here, so this would be, QC. And I'm gonna add to it this, W. All right, so I'm gonna do a couple of things here. First off, this is a totally valid thing right here. Okay, this is a totally valid thing. This is a refrigerator. This is a satisfactory situation for Carnot because this is a cycle interacting with two or more reservoirs and transferring heat and producing, it takes heat in order to do this. It takes work in order to make the heat transfer. This is also okay with Clausius because Clausius says the net result is that I can't just have heat going that way. I have to make it happen that way. So Clausius is also okay with this. This is just a standard refrigerator, and this is totally okay. We already know this violates both the first law and the Carnot second law, so we can say that, but let's suppose that it's true. What happens when we add those? So I'm going to make a cycle adjustment such that this work and this work are exactly the same. And therefore you can see that when I do that, what I'm going to get out is a cycle whose only result is to transfer heat from cold to hot. And this is a way in which I can say, well, if that was true, then this would be true. But this violates Clausius' second law. Therefore, this violates Carnot's second law. That one does. Because we know this one's fine. That one does. Which we knew already. Or you could do it the other way. I know this is not true, but let's pretend that it was. That means I could do this, but I know that's not true, so therefore this is not true. Okay? And this is a violation of the Clausius second law statement. Now, there are a bunch of different ways that you can go through and do stuff like this, and you can ultimately look at a bunch of different Carnot exclusions and possibilities. And you could find that the addition of cycles like this, I made a cycle adjustment such that these works were the same, and I'm adding the two cycles to get a net cycle. What I've done here is I've done one instance in which I'm showing that the Carnot statement is equivalent to the Clausius statement. Okay. This is only one example. Obviously, I could pick many different ones over here, but ultimately it all seems to work out the same way. And so what I can draw from this is, hey, the Carnot statement is equivalent to the Clausius statement. Now I have to do the opposite, in which I have to say, I got to take the Clausius statement and show that it's equivalent to the Carnot statement, so that just because one goes one way doesn't mean the other one can't subsume it the other way, right? I have to show that they both deny the exact same thing. And so I guess I will pick up with that on Tuesday. Yeah, on Tuesday. Just by way of reminder, folks, there's no PLC this week. There's no going to be no lab tomorrow. And so we're free and clear until next Tuesday. So I wish you a happy weekend and good joy and tidings thinking about second law ramifications. I'll get homework 5 posted so that you have it and are ready to get going on it. And we'll go from there. Alrighty, happy weekend. See you next time.